Oh, yeah, right here. Yeah. Thanks. Okay, let's go out to for those of you Zooming, the in-class assignment should be available there. Let's see. Okay, we're going to cover section 6.1 and 6.2, where you have multivariate functions. So you can see here, we have the function, the natural log of x plus y cubed, and there are two variables there. And we're going to evaluate this function at e to the 5, 7. E to the 5, since it's listed first, corresponds to x, and 7, since it's listed second, corresponds to the y. So you just plug those values in for x and y respectively. And hold on, let me copy this down before I, let's see, we have natural log of x plus y cubed. And we're evaluating at f e to the 5th, 7. Just a minute, let me get my screen set up properly. There, that's better. Okay, so we just take e to the 5th and plug it in. Well, natural log of x becomes natural log of e to the 5th. And then 7 for y gives me 7 cubed, and I'm adding that. So you can see I just replaced the x with e to the 5th, and I replaced the y with 7. And then I can just calculate this. I'm not sure what format they wanted in. I think it's it might be multiple choice. No. First of all, natural log of e to the 5th is just 5. And then 7 cubed, let's see, 49 times 7 is going to be 63. 28 plus 6 is 34. So 343 plus 5 is going to be 348. Okay. Now, the next 3 problems come directly from your homework, and I always like to do these in class for students because I find that a lot of students, they're not too difficult. It's just they're not sure how to handle the situation. So we have a function here, h of xy is equal to 5x e to the square root of 3 plus y. And we are asked to define the domain. And when you're looking for the domain, the two things that cause problems are radicals. You can't have the radical of a negative number, and denominators. So you can see here we have a radical. So any real number will work. And in this case, because we have two variables, we're talking about any ordered pair, where x could be any real number and y could be any real number, except we must require that 3 plus y is greater than or equal to 0. So the way we write that is we write the domain is the set of all ordered pairs x, y, such that 3 plus y is greater than or equal to 0. This is set builder notation. We cannot use interval notation because interval notation is only for a number line, right? And that's one variable. Now we have two variables, so we're forced to use set builder notation, but this is how you would write it. And you would generally want to solve for y in this context. So I would subtract 3 from both sides of the inequality. And that gives me d equals the set of all x, y, such that y is greater than or equal to -3. So C is, let's see, or D is the correct choice, where see here it says y is greater than or equal to -3. So that's good. Okay, again, we have in this function a radical, fxy equals the square root of y plus 4x. So we're looking for the domain, and we just require that, well, it's going to be any ordered pair x, y, but with the restriction that y plus 4x must be greater than or equal to 0, because that's the radicand. Y plus 4x is the radicand. That's what's under the radical. We require that be greater than or equal to 0. And I'll go ahead and solve for y. So I subtract 4x from both sides. And I get that d equals the set of all x, y, such that y is greater than or equal to -4x. Okay. And I think this one we have to enter in. So we're just going to write y is greater than or equal to -4x. And finally, we have a situation where we have a denominator. So this time we have g of x, y equals 1 over y plus 6x squared. And any ordered pair works except for the one where the denominator is 0. So we're going to express the domain then as the set of all ordered pairs x, y, such that y plus 6x squared is greater than or, I'm sorry, not equal to 0. It can be greater than or equal to 0. It's just that we have a denominator here instead of a radical. So it cannot equal 0. So generally we like to solve for y. So I'm going to subtract 6x squared from both sides. I think it's okay if you put it in like this, except for when you look at the answer, they have y isolated. Let me show you in just a moment. So I'm going to write this as the set of all x, y, such that y is not equal to -6x squared. Okay, and if you look at your answer, you can see right there, they have y not equal to, so -6x squared is the only correct answer that will work. Any questions on those three? So those are finding the domain of multivariate functions. It's pretty much the same as single variate. It's just you got that one added situation where you have two variables. But generally, we just isolate the y, and that will get you where you need to go. Okay, the next section is the section where we're going to be introducing partial derivatives. What is a partial derivative? When you have a multivariate function like we do in this example, we have f of xy equals the square root of x squared plus y squared. We want to be able to differentiate, but they're two variables. So what we do is, if we want to differentiate with respect to x, then we just treat y as a constant. And if we want to differentiate with respect to y, we treat x as a constant. So let me show you how that works. So the notation is like this. We have our multivariate function, and we use this script d. That is actually a d, not a 2. We're differentiating with respect to x, but I'm using a script d because we're doing a partial derivative, because this has got two variables in it, and we're just differentiating with respect to one variable at a time. So the notation that we use for this is f with a little x. This just tells you how you're differentiating it. And because I'm differentiating with respect to x, y squared, this y here is treated like a constant. So think of this as x squared plus y squared to the power of 1/2, right? And then when I differentiate, applying the power rule, the 1/2 comes out front. And then I subtract 1 from 1/2 to give me -1/2. And then by the chain rule, or the extended power rule, I have to multiply by the derivative of what's inside. But I'm treating this as a constant because I'm differentiating with respect to x. So when I take the derivative of this, the derivative with respect to x of x squared is 2x. So I'm going to multiply by 2x. But the derivative with respect to x of y squared is 0, because this is treated like a constant. So we have then, the negative means it's going to go in the denominator. Notice the 2's cancel because I have 1/2 times 2, that's just 1. And my x is going to be in the numerator. So this becomes x over the square root of x squared plus y squared. And then I think in the problem it asks us to evaluate at 2, 3 for fx. So I'm going to take the 2 and replace x with 2, and then I'm going to replace y with the 3. So this becomes 2 over the square root of 2 squared plus 3 squared. So here's x, that becomes a 2, this becomes a 2, this becomes a 3. And then we have square root of 13. Normally we would rationalize the denominator, but I tested it earlier and they accepted this as an answer. But normally we would multiply top and bottom by the square root of 13, and we get 2 square root of 13 over 13. But like I said, they accept this as an answer. So either one is valid. Okay, the next thing we want to do is we want to calculate the partial derivative now with respect to y. So that would be fy, little y. And now we treat x as a constant. So when I take the derivative, applying the power rule, I get 1/2 x squared plus y squared to the -1/2. But then when I take the derivative of what's inside, x squared is treated as a constant. Okay, so we're going to multiply by 2y. And the 2's cancel, and I get y over the square root of x squared plus y squared. And then when we evaluate that, I forget the number that we're supposed to plug in. We're plugging negative 5, 4 in this time. And so that becomes, the y is 4, and then the square root of negative 5 squared plus 4 squared. Let's see. 25 plus 16, 41. And you can write that as 4 square root of 41 over 41. But like I said, they accept either answer. Yeah. So plugging this all in, we get x divided by square root of x squared plus y squared. And then we get y divided by okay. So let's do another example. Here we have fxy equals minus 3e to the 2x minus 3y. Now notice this is an exponential function. How do I know that? Well, notice that the exponent has the x and the y in it, so that means it's the variables are in the exponent and the base is a constant, so that makes it exponential. And I'm differentiating first with respect to x, and then I'm going to differentiate with respect to y. So, but we use the same rules. So when we differentiate with respect to x, like I'm doing here, we treat y as a constant, but the rules still apply. You copy what you see, so you get negative 3e to the 2x minus 3y. Multiply by the derivative of the natural log of the base. Well, the base is e, so the natural log of e is just 1. We don't have to worry about that. But now we multiply by the derivative of the exponent. But y is treated as a constant. So the derivative of 2x is just 2, but the derivative of negative 3y is going to be 0. So we multiply by 2. Now, the second time around, we're going to differentiate with respect to y. So we copy what we see. Then we multiply by the derivative of the exponent, but this time we treat the x as a constant. And so this becomes Oh, then we multiply by the derivative of this. This is 0. The derivative of this is 0, but the derivative of negative 3y with respect to y is negative 3. And so we have 9e to the 2x minus 3y. So we get different answers because we're differentiating here with respect to x and here with respect to y. Okay. All right, that concludes our in-class assignment, but I would like to turn our attention now to the homework because the homework is kind of tricky and it's due tomorrow night, so I wanted to kind of go over it for you. I'm talking about 6.1 is pretty straightforward. You're just plugging in numbers, right? And it's a short assignment. I think there are only 11 questions, and you're just taking these numbers like 5, 0, x is 5, y is 0, plugging them in and calculating a number. It's pretty straightforward. Let's see here. But going back to 6.2 assignment, all right, here we have partial derivatives, and I did some examples, but I want to go kind of skip forward to where we have 4 sets of second partial derivatives. Okay, so here we have a function and it says find the 4 second order partial derivatives. Let me write down this function and I'll show you how to do that. All right, so the 4 partial derivatives are, well, we have fx and fy, but then we can differentiate each of these functions with respect to x and y. So you get fxx, fxy, and then you get fyx and fyy. So these are your 4 second order partial derivatives. Remember, second order derivatives, you differentiate twice. So here, you're differentiating with respect to x and then with respect to x again. Here, you're differentiating with respect to x and then with respect to y. Here, with respect to y and then x. And here, both times with respect to y. So let me show you how we do that. So the first time, I'm going to treat y as a constant because I'm differentiating with respect to x. So this we treat them as constant. And so I'd like to write this, let me rewrite this function. With the constants grouped together, I think that will help you understand what I'm doing here. So since this y is a constant, I'm going to group it with the 5. So I have 5y times x to the 9th. So we're treating this as a constant. Then I have minus 2y times x, and this gets treated as a constant, and then, of course, 9y, the whole thing is a constant. Okay, so when I differentiate this last one, that's going to go to 0 because I'm differentiating with respect to x. So here we have fx is equal to, well, I take the 9, multiply by 5y, that becomes 45y, and I subtract 1 from the 9 to get x to the 8th, like that. Now notice I have a constant times x. Well, the derivative of that is just your constant, which is your slope, right? Because that's a linear. So I have negative 2y there. And then finally, this is a constant, so it's 0 when I differentiate it. So here's my first order partial derivative with respect to x. Now I'm going to copy my original function down again because I want to circle the other constants. So I'm going to write this as fxy This is my original function, but this time we're differentiating with respect to y, so the x's are going to be held constant. So that means these are my constants. Okay. So I have a constant times y, a constant times y, and a constant times y. So in each case, those are linear because the power on y is just 1. So I just have the constants when I differentiate, right? So this becomes 5x to the 9th minus 2x plus 9. Does that make sense? Any questions there on that?
Can you go over why, can you explain where you dropped the 2 y's from the 5x to the 9 minus 2x?
This one?
No.
Or no, right here.
Yeah.
Okay, I know it's confusing. Let me take an aside and kind of do something you already know. All right. So when I say differentiate, so here we have a function. It's confusing because we often write y equal to something like 3x plus 2. This y, though, is a dependent variable, whereas the y in these problems are independent. So it's a little kind of we're changing. So think of this as f of x. Okay? When we differentiate this, so an f prime of x, what is the derivative of that?
3.
Right. Okay. Well, let's extend that over now to, here we have our function 5x to the 9y minus 2xy plus 9y. Basically, what we have here is, here the independent variable is an x. Here the independent variable is a y. So the constants, it's linear, right? This has a power of 1, this has a power of 1, this has a power of 1, this is a power of 1. When you differentiated this, you just took the number, this piece right here, you just took the number out front and wrote it down. And that's what I'm doing there. Because these are all constants times y. And so when you take the derivative with respect to y now, you just write the constant in front. It's tricky, but it's... We're kind of, because we added a new variable, our dependent variable now is z, where I'm not writing z, but it's a different variable. The y is now lumped in with the x. It's kind of treated the same way, kind of like as an x.
So pretty much, if the variable is, for the second one, the one that you're circling green, if
Those are the constants. The variable is y.
So when the variable is y, it doesn't have an exponent like the x does on the top with the 9.
Exactly.
It drops.
Exactly.
Okay.
Yeah.
I see what you're saying.
Yeah. Yep.
But if it's on the inside.
Because if you think about it, what is the exponent here? The exponent is 1. Well, if you subtract 1, you get 0, and y to the 0 is just 1, and anything times 1. So you would have 5x to the 9 times 1. It's just that.
But if that 5x to the 9th was just 5x, you still bring down the 5x because it's on the inside, and that's the constant.
Because we're differentiating with respect to y. Well, whereas up here, we were differentiating with respect to x. So we treated y as a constant, and that 8 came out front, and then we subtracted 1 from the 9 to get the, the 9 came out front, and we subtracted 1 from the 9 to get the 8. Yeah, but that was because this showed us we're differentiating with respect to x. Okay, so now we have these new functions here. Now we're going to differentiate these, each one with respect to x and then y, so this little x here refers to this x, but we're going to differentiate it with respect to x and then y, just kind of like what we did for this one up here. And then this little y refers to this y, and then we differentiate that with respect to x and with respect to y. And by the way, the notation that I use, so this is when you differentiate with respect to x, you use a script d instead of a regular d to show that it's a partial derivative. So this becomes the derivative with respect to x of my new function here, which is the 45yx to the 8 minus 2y. So now I'm differentiating this with respect to x. So since it's with respect to x, the y is constant. So this is going to be a constant, and this is going to be a constant. And so when you differentiate that, the 8 is multiplied by the 45, so that's going to be 360 y. The y is kind of included in that because it's constant. X to the 7th, because I subtracted 1 from the 8. And this is just a y in there, so there's no x in here, so this is a constant. So when I take the derivative of that, it's 0. Okay. Oh, someone's asking a question in the chat. Yeah, I can do that. Can we do that at the end of class? I'll come back to that. Okay, so let me just enter this in to make sure that I don't, I just want to make sure I'm doing it correctly because there's so much going on. So I did xx, that's 360y x to the 7th. X, oops, 360 times y x to the 7th. I just want to make sure I didn't make a mistake. Good. Okay, now the next one, we're going to go, we're taking the derivative with respect to y of fx. So that's the derivative with respect to y. Well, what is fx? We found that up here to be the 45yx to the 8th minus 2y. So it's the same thing here. But see, now we're differentiating with respect to y. So the x to the 8th is a constant. So I'm just going to rewrite it in a different order so that I can group the constants together so I don't get confused. So I'm going to put the x to the 8th with the 45. And then I've just got a plain old y. And then we have the minus 2y like that. And so now I just have y and y with constants in front. So when I take the derivative with respect to y, I just write down the constants in front. So it becomes 45x to the 8th minus 2. Because these are held constant. Those are the constants. So I'm going to go ahead and enter that into the 45x to the 8th minus 2. Now the interesting thing, I'm not exactly sure why it works that way, but when you take the derivative of this y with respect to x, you're going to get the same answer here. It's a nice little way of checking to make sure you're doing it right. So when I do it the reverse order, in other words, I take my fy function and differentiate with respect to x. I'm going to put this up like that. Okay, now I'm looking at fy. Here's fy. It's 5x to the 9th minus 2x plus 9. So y doesn't even come into play here. So you're just going to differentiate this with respect to x like you normally would. And so it becomes 45x to the 8th minus 2. And voila, you get exactly what I got here, just like I said I would. So that's kind of a neat little thing there. And then now we're going to do this same function, but this time with respect to y. But this time, since there are no y's in here, this whole thing is constant. So the derivative of a constant is 0. So you get 0. Okay. Same thing here. Hold on. I'll just do one more example here. So we have fxy equal to 7x to the 5th, y to the 6th plus 2x to the 4th, y to the 7th. So with respect to x, now I treat y as constant. So this becomes 35x to the 4th, y to the 6th, plus 8x cubed y to the 7th. Notice that the y to the 6th and then a y to the 7th did not change. That's because those are constant. But now I'm going to differentiate with respect to y. So this time I take the power on the y and multiply it by the 7. It becomes 42x to the 5th, y to the 5th, plus 14 x to the fourth y to the sixth. Notice the x's did not change. Whoops. Yeah, I'm doing this one up here. I have x to the fifth, x to the fifth, x to the fourth, x to the fourth. Those did not change because those are constant. Now I'm going to take the derivative with respect to x of this right here. So I'm going 4 times 35, that's going to be 140 x cubed y to the sixth plus 24x squared y to the seventh. The y powers don't change because they're constant. But now with respect to y, they will change. This becomes 6 times 35 is going to be 210 x to the fourth y to the fifth. And then 7 times 8 is 56 x cubed y to the sixth. So now this first letter here, this y, means I'm going to take this function and differentiate it with respect to x. So that becomes 210x to the fourth y to the fifth plus, differentiating with respect to x, so it becomes 4 times 14, that's 56 x cubed y to the sixth. And notice I get exactly the same thing here. These match. That's always going to, or not 100%, but almost 100% of the time will match. And that's kind of a check that you can use to make sure you've done it correctly. And then finally, we're going to differentiate that with respect to y, this one with respect to y. And I get 210x to the fifth y to the fourth plus 84 x to the fourth y to the fifth. Okay. So it's kind of tricky, but just, practice, I guess, is the best thing. And I'm not going to take the time to enter those all in. Well, maybe I should, just to be on the safe side. 140 x cubed y to the sixth. Did you have a question? Anybody? Okay. All right. Okay. And then we have 210x to the fourth anyway, it looks like I've done it correctly here, so, oh, as soon as I say that, hold on, did I copy the right one here? Oh, they wanted YY, and I put in XY. 210x to the fifth, x to the fifth, y to the fourth, plus 84 x to the fourth, y to the fifth. Okay, I'll just let you finish that. So let's answer your question. Was it Cade that answered that or asked that question? Let me go back to the homework assignment or I'm sorry, the in-class assignment real quick. Which question was it that you wanted me to do? I wonder if he's still here. Cade, which one?
Yeah, I'm here. So it was number 4 on the class assignment.
Okay, what was your function?
Determine the domain of the function of 2 variables.
Right.
And with yours and your numerator, it was 1 and mine is 2. So I didn't know if that like required anything different.
It does not.
Okay.
Because the 2 is just, is not, the denominator is the one that you're focused on. So you're going to say, when y is not equal to negative x squared. In other words, you take your denominator and set it greater than or not, I'm sorry, you set it not equal to 0 because you don't want your denominator equal to 0. And they just move the x squared to the other side of the non-equation, if you will, not equal.
Okay.
Does that help?
Yeah.
Okay. Any other questions before we end class? Okay. Then we have no class on Friday, no Zooming or in person. So I guess hope you have a good break.